Hello everyone. In the previous video we have seen Schrodinger's time independent wave equation, and now we are going to study one application of this independent wave equation, that is particle trapped in one-dimensional infinite square well potential. Now this is the case. This particle is trapped along a line, that means it is one-dimensional. This particle cannot cross this barrier, cannot cross these boundaries. In order to cross these boundaries, it requires an infinitely large potential. So it is infinite square well potential. We have just considered one dimension, so particle trapped in a one-dimensional infinite square well potential. The example for this we can consider as a free electrons in metals. These free electrons can move across the surface, so it becomes two-dimensional, but these electrons, they cannot cross the boundaries of metal unless and until large potential or large energy is given to them. We can also consider the electrons that are trapped in junction in a diode. Okay. So here this particle is just moving back and forth within this potential well. Now this potential well, inside the potential well, the potential is 0, and outside potential is not equal to 0 because it requires a very large potential. Now as particle is moving inside the well, it has a wave associated with it. So as this particle has a wave associated with it, this wave function psi cannot be 0 inside the well. But outside the well, particle is not present, and therefore wave function psi is equal to 0. So remember, this wave function represents the probability of finding the particle. As particle is present inside the well, psi is not equal to 0. As particle is not present outside the well, psi is equal to 0. So this particle is trapped in a well and it is in bound state. So energy of particle is independent of time, and therefore we have to use Schrodinger's time independent wave equation to find out energy of the particle. And inside the well, V is equal to 0, and therefore this time independent wave equation becomes dou 2 psi by dou x square plus 2m by h cross square. E, V is 0, so E psi is equal to 0, and this is for this well, that is 0 less than x less than L. So this is the dimension of the well. Now we know that K is equal to P by H cross. We have seen this in time dependent wave equation. We have put K is equal to P by H cross. So P is equal to H cross K, and we know that total energy E is equal to P square upon 2m. Here V is equal to 0, so just P square upon 2m, and P is H cross K, so it is H cross square K square upon 2m. So from this equation we can write K square is equal to 2m E by H cross square, and therefore this 2m E by H cross square we can replace by K square. Okay, so this equation becomes dou 2 psi by dou x square plus this is K square psi of x equal to 0. Okay, so this is our equation 1. Dou 2 psi by dou x square plus K square psi equal to 0. Now this equation is just like simple harmonic motion, equation for simple harmonic motion, and therefore we can write solution for this as psi of x equal to a into e raised to I kx plus b into e raised to minus I kx, since the particle is moving in positive x direction and negative x direction. Okay, so this is the solution for equation 1, and this is our equation 2. Now let's apply boundary conditions. So first boundary condition is x is equal to 0. Now at x is equal to 0, particle is not present at boundary. Here particle is not present at boundary conditions. It is not present at 0 or not present at L. Okay, and therefore at at 0 and at L psi is equal to 0. So putting this at boundary condition, x is equal to 0, psi of x is equal to 0, and therefore this psi of x is equal to a e raised to I kx, again 0 because x is equal to 0. So a plus b, which is 0 because psi of x is equal to 0, and thus a is equal to minus b, or b is equal to minus a. So putting this into equation 2, we get psi of x equal to, here b is equal to minus a, so a into e raised to I kx minus e raised to minus I kx. But e raised to I kx is cos kx plus I sin kx, here cos kx minus I sin kx. Okay, so cos kx minus cos kx gets cancelled out, and we get psi of x equal to 2ia sin kx. Now let's apply boundary condition, second boundary condition, x is equal to L. Now as we know, at x is equal to L, again psi of L is equal to 0, and 2ia sin kl is equal to 0. 2ia is constant, so it cannot be 0, so sin kl is equal to 0, and when this sin kl is equal to 0, when kl is equal to n pi. So kl is equal to n pi, and thus we can write, but as we know, k is equal to 2 pi by lambda, and from this k is equal to n pi by L. So from this 2 pi by L, 2 pi L by lambda is equal to n pi. Here I have just replaced k by 2 pi by lambda, and thus we get 2 pi L by lambda equal to n pi. Pi gets cancelled out, and we get lambda, taking this lambda on this side, lambda is equal to 2L by n. So using this equation, we can find out wavelength of the particle. Lambda is equal to twice L by n. But we are interested in energy. So this n is equal to 1, 2, 3 and so on. It is just integer. Thus the particle forms. So from this we can write this. If we take n is equal to 1, then lambda is equal to 2L. If we take n is equal to 2, then lambda is equal to L. And thus we can say that particle waves forms standing wave pattern within the potential box. Now momentum P is equal to h cross k, we have just seen, and energy E is equal to p square upon 2m. Here k is n pi by L, from this n pi by L. So and h cross is h upon 2 pi. So h upon 2 pi into n pi by L equal to pi gets cancelled out, nh upon 2L, and energy E is equal to p square upon 2m. P square is nh upon 2L square, that is n square h square upon 4L square into 2m. So final energy equation is n square h square upon 8 ml square. N is again 1, 2, 3, 4 and so on. So first energy E1 is equal to n is equal to 1 h square upon 8 ml square. E2 is equal to n square becomes 4. Okay, 4 2s are 8. So h square upon 2 ml square is the second energy value. Third energy E3 is equal to 9 h square upon 8 ml square. Okay, and these are the probable energy values and wavelength values. Okay, so this is our particle trapped in a one-dimensional infinite square well potential. Here when n is equal to 1, this is our energy E1, that is h square upon 8 ml square. So when n is equal to 1, lambda is equal to 2L. Okay, so L is equal to half of lambda, and therefore again standing wave but half a wave. And here as at the center it is having maximum amplitude, the probability of finding the particle at center is maximum when energy is h square upon 8 ml square. When n is equal to 2, for this, when n is equal to 2, lambda is equal to L. Okay, so L is equal to lambda, and energy becomes h square upon 2 ml square. Okay, now here you can see as the L is equal to lambda, you can see full wave, and therefore the maximum amplitudes are at the centers of left half and right half. So probability of finding particle is maximum here at the center of left part and right half of the potential well. When n is equal to 3, the probability, of course, lambda becomes 2L by 3. So you can see 3 half waves, and probability of finding the particle at the center of well, at the center of left half and at the center of right half is maximum, and energy is 9h square upon 8 ml square, and so on. So this way we can find out probable positions of the particle from maximum amplitude, we can find out wavelength, we can find out energy of the particle by using Schrodinger's time independent wave equation for this particle trapped in one-dimensional infinite square well potential. Hope you have understood this derivation and application. Thank you so much.